like what was the idea was that whenever like we are given a feature vector x, then in normal classification like say k nearest neighbor or decision tree, like what we are doing is we are mapping it to a label y where which is part of the label space. This is what was we had done so far in normal classification. Now in probabilistic classification, what we do is we take a feature vector x and we map it to a probability distribution over the label space. Okay, that means to say like for everything or every element in the label space, we get a probability value that, say for example, if it is a like a cat dog classification problem, we or like a binary which is essentially a binary classification problem, like our output will be some probability distribution like this 0.7, 0.3. Means 0.7 is the probability of cat, 0.3 is the probability that the feature vector corresponds to a dog. Similarly, if instead of binary, if it was like say some 5 class classification, then also the probability distribution will be something something similar to that, maybe something like this. Right? But whatever it is, it will have to be a valid probability distribution. That means that all the things will have to add up to 1 and all of them should lie between 0 and 1. So like so pi, sorry, let me call it as pk. Pk must lie between 0 and 1, and if you sum over all the pk's, you will get 1. Okay, so yesterday what we are doing is that we were trying to parameterize this kind of a probability distribution. So this is a probability distribution which we are interested in, the probability distribution of the labels given the features. Okay, so this we are trying to parameterize, and we parameterized it as some kind of a something like this. Okay. This is in case of a this is what we did in case of a binary classification. In case it was like some like k-way classification, then we parameterized in the following way. It will be proportional to, is proportional to, no, in this case it is equal to, then this is wk transpose x. Okay, so we like this is the way we wrote it, and then for like this is true for, so basically the parameters are the wk's for the different classes, and of course this is proportional, so like we'll have to normalize it by an appropriate proportionality constant, and we saw what that value of it must be. Basically you just have to add up these things for the different values of k. So so this is like this is what we did in the last class. Now today we will like do or we'll take this forward without having to parameterize the this distribution in this particular way. So for that purpose, let us focus on this distribution. What is this saying? It's saying that you have got a feature vector, you have already got a feature vector x, and this is like what you have observed, and based on that you are trying to calculate what the like what is the probability that the corresponding label is equal to k. So you are basically trying to calculate the probability of this thing, of this label being equal to k after observing the feature vector which is x. Okay, so now let us go in. Now before going before analyzing any further, let us recapitulate what is Bayes theorem. So anyone can tell me Bayes theorem? Suppose you have two random variables a and b. So based on a and b, what does Bayes theorem tell us? Anyone can tell?
P of A given B equals to P of B given A time upon times P of A upon P of B, or P of A intersection B upon P of B.
Is this right? Is this what you said?
Yes, sir.
Okay, fine. So this is what our Bayes theorem is telling us. So what does it say? It is saying that suppose A and B are both random variables. Okay, so we all know what is random variables. So now what it is, what Bayes theorem is saying? It's saying that the probability of A given B. So so what is meant by probability of A given B? So that is A and B may have some interrelations among them. A and B in general may not be independent. They like whatever value B takes, we may have some bearing on A, what value A will take, and vice versa. Now suppose we are interested in understanding what is the or what is the probability that A takes any particular value. Okay, or we basically we want to understand the probability distribution of A. Okay, now suppose so the probability distribution of A is of course encoded by this quantity, right? P of A. This is nothing but the probability distribution of A. Now, so this is the just the probability distribution of A independent of any other thing, any other influence. Like whatever values like other variables may take. This is this is not taking all of that into account. It is just giving you just telling you the probabilities of the different values which the random variable A can take. Now, but I have said that B does or may influence A. Now, suppose B, you already know that B takes a particular value. Let us say small b. Okay, let's say we already know the value of the random variable B. Then what can we say about the distribution of A? So, so one is P of A, that is the probability of the random variable A in when we do not know about have no other information. The other is P of the probability of A given that the random variable B takes some particular value, maybe small b. Like what value it takes maybe is not important, but the thing is that you already know what value this random variable B takes, and then you are trying to get an estimate on what value this A is going to take. Okay, so so clearly, so obviously these two things are not the same. Probability of A can happen for different values of or various possible values of B, but here we are talking about what will be the value of A for one specific value of B. So right, so so this kind of probability distribution, what is it sometimes known, or what is the name of this kind of probability distribution where this a notion of given is there?
Conditional probability.
This
Conditional
is
probability.
this is called conditional probability of A given that or given B. That is B is the condition and A is like the target whose probability you are trying to measure. So this is a conditional distribution. And what is this called? Anyone knows what this is called? P of A, where nothing else, no other, only one variable, where nothing else is there. This is called the marginal distribution.
Right.
This is called marginal distribution. And so now if I multiply P of A given B times P of B, that is I am multiplying the conditional distribution of A given B with the marginal distribution of B, then what do I get? Of course, like from Bayes theorem, we know what we get. Like I can just rearrange the terms and give you the answer. But apart from that, what else do I get?
P of A intersection B, sir.
A intersection B. Don't use the language of set theory here. We are dealing with random variables.
Joint distribution.
A and B.
Yes, A and B. This is the joint distribution. right? So there are three kinds of distributions. One is the conditional distribution, one is the marginal distributions, the other is the joint distribution. Okay, so as of now we are not talking about joint distribution in the Bayes theorem. The Bayes theorem is basically giving you the relation between conditional distributions and marginal distributions. Okay, so what it is saying? It is saying probability of A given B times probability B, just if I write it here, if I bring in this here, is equal to probability B given A times probability A, and both of them are equal to, of course, the this joint distribution of A and B. So you can, the same joint distribution, you can write it in this way, or you can also write it in this way. Okay, now if the following, so in general this marginal and this conditional will so like here you can see that this is a marginal distribution over random variable A, this is also a distribution over random variable A, but this has a condition, but both are distributions over the same random variable A. Okay, so if it happens that these two distributions are exactly the same, then what can we say? If this happens, then what can we say?
That A and B are independent.
Then we say that A and B are independent, right? Sorry, A, B independent. Okay, now now with this quick recap of probabilities, let us come back to this particular observation. Now let us like if you consider the previous case or yesterday's class, like it seems that this y, the label of any given example, is a random variable. That is how we are treating it. That is like we are consider that given any feature vector, the feature vector is a fixed quantity, but give like once we know the feature vector, we are pretending that this the corresponding label y is a random variable and we are measuring its probability distribution. Okay, now suppose now like in the previous treatment, that's what we had assumed, that this is an RV. Now today let us assume that the feature vector x is also an RV. It's also a random variable. It's a that is to say there is some probability distribution. Let's call it as Px. This is a probability distribution over the feature space. Distribution over feature space, and whatever value or whatever feature vector you are observing is like is a realization of this probability distribution. Okay, it's like or it's a realization of this random variable. Okay, okay. So now so x y are both random variables in this, in like the way we are treating it. So now what happens to this particular quantity? Like yesterday we are writing this probability of y given x. At that time when I talked about y given x, I did not really mean that x is a random variable. We meant that like x has some value which we know. But here I am considering that this x is actually a random variable whose value I have observed. Okay, so now according to Bayes theorem, we can like clearly we can write. Yes, anyone saying anything? Not your. It's not clear what you are saying. Okay, so this is what the Bayes theorem is saying, right? So if you just import like this is what Bayes theorem says. So what and now so let us say that, let us consider this as a constant for the time being. Okay, let that be. Why? Because x is something which we have observed. That is although it's a random variable, but its value we have observed. So like this thing we can like, let us say that we can calculate it. It's fixed. What we do not know is y. So it's really y with the which is of interest to us. So let's treat this as a constant, and so let us write this as probability of y given x is proportional to probability of x given y times probability of y. Okay, so this is the major like the important part of the thing of the algorithm which we are going to study today. So let me write this afresh. If you consider the first term on the left side, probability of y given x, that is telling it is basically telling us what's the probability of the or what is the probability distribution of the labels once we have already observed the features. Okay, and that we are telling is proportional to p of x given y times p of y. Okay. Now p of so clearly this is something we need to calculate. Now let us look at the things on the right hand side. So what is p of y? P of y is basically telling you what is the probability that the label takes any particular value, right, irrespective of any features. That is, suppose you have not seen any feature at all, then what is your or then what is the or what you consider as the probabilities of the different labels. Okay. So suppose so any estimate about or any idea about how this p of y can be estimated? Okay, let me show you a sample data set.
A particular label space, or a particular member of the label space divided by the whole label space.
Right. So let us look at this. So let us say that here is a particular data set where the the label can take 4 possible values, and let us assume that there are 200 such labeled examples which you have. So now so remember that we have not observed x at all. So if we have not observed x, forget x and concentrate only on y. So now in this data set, we find that there are out of 200 examples, there are 80 examples where y is equal to 1. Right? Yes, relative frequency. If then y is, there are 80 examples where y equal to 1. There are 50 examples where y equal to 2, 40 examples where y equal to 3, and so on. So basically you can just calculate the relative frequencies of the different class levels, okay, from the training data set. So this distribution is sometimes known as the or is it is known as the prior distribution. Why is it called prior? Because prior means what? Prior means in front or before. Like before what? Before observing the features. Before observing features. Now, so if this is to be called prior distribution, then what this is saying is that what is the probability distribution on y after observing the features. Okay, probability of y given x. You already know what x is, and based on that you are trying to estimate this distribution on y. So this is called the posterior distribution. Posterior means what? Posterior means behind or afterwards. So after what? After observing the features. Now what about this part? So what is meant by probability of x given y? So here first to make sense of this quantity, let us understand what is meant by a generative model. So generative model is basically a story about how the data was created. Okay, a story about the origin of the data. So what is the data? That there are two parts in your data. One is the X part and the other is the Y part. So let us say this is your data set. You have n examples. Each example consists of an X part and a Y part. And so okay, so now you so now I am, what I am going to do is I am going to tell you a story about how this data set was created. So the story is as follows. The story is that first its label was chosen by someone, say by the creator. The creator, I mean the creator may be a creator of the data set, or the or just some or god or some supernatural entity, something. Let us just say that there is someone called some creator who has created this data set. Now what the creator did is that for every example, each of the n examples, first of all that creator created yi. How did the creator create yi? That is by sampling from the prior distribution. So we already know what is so suppose we already know that this is the prior distribution on y. So like we already know how to estimate it. Let us say that prior distribution is already known to the creator. So so what the creator did is, the creator basically rolled a dice, an unweighted dice, where an unweighted dice with k faces, where each face has the probability of p small k. Okay, so like let us say p1, that is p1, p2 up to pk. So what the so total capital K number of faces are there in this dice, and each face has a probability small p of I mean small p1, small p2, etc. of turning up. So the creator rolled that fictitious dice and got some number. So maybe that number was 7. So basically yi, the it's basically the, in that case it will be the 7th level. Okay, so basically this way the label of this data point was chosen. Now based on that, the features were created. That is, xi was then chosen based on a particular distribution called x given y. So it's like, so again, if we are coming back to the cat dog classification problem, so let us say the attributes involved in this case are let's say weight, color, and what else, let's say height. Okay, so so the label space in this case actually just consists of cat and dog. So what the creator of the dataset did is that first of all the creator like tossed a coin to decide whether this particular, the ith example, is going to be a cat or a dog. So suppose the answer came to be cat. So yi was written down as cat. Okay, or cat, or like if it is to be represented in the 1-0 representation, and cat is stands for 1 and dog stands for 0, so yi in that case took the value of 1. Now what is going to happen? Now the features are going to be created with the knowledge that this is a cat. So so the weight feature, when I am sampling the weight features, I will sample from a distribution which is typical of a cat. That is, I will probably never sample a values like say 30 kg or 35 kg or 55 kg, because these are not possible weights for a cat. So I will focus on only those values of, or only such a distribution of weights which are feasible for a cat, and I will sample one such value, let us say 12 kg. Then similarly color, I already know what are the possible colors of a cat, so I will sample from one of those colors. Height also, I am never going to sample something like say 6 feet or 9 feet or anything like that, because that's not a possible height for a cat. So whatever is the possible height for a cat, I will sample a value from there. Okay, so this is so like first of all, so basically I do two rounds of sampling. I sample the label first and from the prior distribution, and then based on that sampled value, I sample the features from this kind of a distribution, which I also call as the class conditional distribution. So this is sometimes, so this is called class conditional. So note that while the prior and the posterior, both of them are distributions over y, that is to say they are distributions over the label space, but this probability x given y, this is a distribution over feature space. So these two are similar, this is different. So this is a distribution over the feature space x. This is a distribution over label space y. This is also a distribution over the label space y. Okay. So now, so what I told you just now, that is the first there is a creator. First the creator decides what the label is going to be, and then the creator decides what the corresponding features are going to be, etc., etc. And the whole thing is done by sampling from some distributions. This is of course a story. It's a story. It's only a story. I mean, it's not. Nobody can say that this is the way our data was actually created. But this way of telling a story is called the generative model, and it's an important aspect of machine learning. Many of the I mean the of course it is not correct that a data set was created like this, but if you make these kinds of assumptions, then it enables you to solve many problems quite easily. Okay, so this is what is known as the generative model. Okay, now comes the question of how we are going to solve our probabilistic classification problem. So let us go back to the data set. So what is the problem? The problem is that I have got a feature vector. Based on that, I need to construct a probability distribution over the label space. I need to give the probabilities of the different classes that this particular example can belong to, given its attributes. Okay. Now, so this is so basically my task is to estimate the posterior distribution. Now, the first, so the as I have already said, the posterior distribution is nothing but the prior distribution multiplied by the class conditional distribution. So how do you get the prior distribution? As many of you have already said it, this is nothing but the relative frequencies. It's the relative frequencies of the different like different labels. So now so this is the way you construct the prior distribution. Now it come to the this class conditional distribution, right? This distribution, that is for a given class level, how do I construct a distribution over the feature space? So let us start it simply. Let us just assume that there is only one feature x, which which takes some values in the range maybe 0 to 30 or something like that. We are starting with a very simple example. So that is, so now for like to make the matter even simpler, let me just divide all the cases, all the 200 examples I have. Let me just divide them into two parts: those who have the attribute value less than 15 and those who have the attribute value of more than 15. Okay, so it may turn out that one set is more numerous than the other, or maybe both of them are exactly equal. So in this case, so let us say that I have chosen this threshold of 15 because it's like the median value. That is to say, there are 100 feature or 100 examples for whom the feature is above 15 and 100 examples for which the feature is, or the feature value is below 15. Okay. Now, let us, those 100 examples in each of the cases, let us break up according to their class level. 100 examples are there, so, and 4 class levels. So each of the, each class level will have certain number of examples. So this is what, that is what information is given by this table. So it's basically saying that among all the examples for which x is less than 15, out of them 40 have label 1, 45 have label 2, 10 have label 3 and 5 have label 4. Similarly, among all the 100 examples which for whom the attribute is above 15, again 40 have label 1, 5 have label 2, 30 have label 3 and 25 have label 4. Okay. So now based on this we again go to the relative frequency calculations. So I can now easily calculate these kinds of quantities. Probability of x less than 15 given y equal to 1. Okay, so what do I want to calculate? I want to calculate these kinds of things. For a particular value of y, the class level, what is the probability that the x takes some value? So here basically what I have done is I have binarized x. So x basically we can take two values. X takes now, although x can actually takes many values, but we have we are considering only two values, either less than 15 or greater than 15. And the question I am asking questions like this, that if y is all, or what that is what is the probability that x is less than 15 given y equal to 2, or what is the probability that x is greater than 15 given y equal to 3? Questions like this is so if I can calculate all these probabilities, then I have estimated this distribution completely. Okay, so that again we can achieve with the help of relative frequencies. So like here, how many examples are there with y equal to 1? There are total how many examples with y equal to 1?
80.
40 here and 40 here. So total 80 of them have y equal to 1. Out of them, only 40 satisfy the criteria x is less than 15. So this probability, like if I calculate according to relative frequencies, is nothing but 40 by 40 plus 40, which is half. Similarly, if I want to calculate this or estimate this distribution, I will do the same thing. Total 40 examples are there, 10 plus 30, for which y equal to 3. Out of these 40, there are 30 of them satisfy the criteria x is greater than 15. So 30 by 40, which is 0.75. So this way, for any given value of y and any given value any given value of x, I mean not any given value of x, but where x is either less than 15 or greater than 15, for any condition on x given this any particular value of y, I can estimate the probability like this. So that means what? That means I can completely calculate this distribution, probability of x less than 15 given y. This distribution I will get completely. Similarly, probability of x greater than 15 given y. This distribution also I can get completely. I can estimate completely. Okay. So, yes, so now once I have done all these things, now how does it help me to get the posterior probability? Because that is what I am finally interested in. Suppose I already know the value of x. So suppose I know that the value of x is in this case 12. Okay. Now the question is, what is the distribution, what values can y take? Okay, so basically I have to calculate the probabilities of the different possible values of y. That is, what is the probability of y equal to a given x equal to 12? What's the probability that y equal to b given x equal to 12, etc, etc. Fine. So, like all the four probabilities of all the four, for all the four values of y, I have to calculate a probability, and that will form my complete probability distribution. Now x equal to, I have not so far not calculated any probability specifically for x equal to 12, but x equal to 12 basically means x less than 15. So let me replace, instead of writing x equal to 12, let me just interpret as x less than 15. Please mute yourself.
है आगे, तो उसमें भी प्रैक्टिकल नॉलेज होना बहुत ज्यादा जरूरी है। और अभी फिलहाल के लिए
Okay. So now, these are the posterior distributions which we are trying to find out. So, right, like these kinds of things. That's what I said. So now, if you have to calculate probability of y equal to 1 given x is less than 15, so now you apply the formula. So what's the formula saying? The formula is saying this is proportional to p of x given y times p of y. So what is probability of x given y in this case? It is nothing but the same thing reversed. What is the probability that x is less than 15 given y equal to 1 times times what? Times p of y, the prior probability. So that is like p of y equal to 1. Okay. Now but this what we are trying to calculate is nothing, is not equal to, but it is proportional to this thing. So that means what? That means a constant of proportionality is also there. So let me write that as k. So I do not know the value of k as yet, but let me just assume that it is k. Okay. So apart from the proportionality constant k, this we have already calculated. How did we calculate it? Where, when did we calculate it? We calculated it here. Right? Like when we are doing these kinds of things, we are calculating it, right? Like a probability of x less than 15 given y equal to 1, we calculated it. So this we already know. Probability of y equal to 1, that also we know. So so like if we read from the database, so we can, like, we will be able to easily calculate all these things. So so let us just as an exercise, let us focus on, say, this one. Probability x is less than 15 given y is equal to 2. So what will its what will its value be? So first of all, let us see how many of the examples satisfy y equal to 2. So I see that there are 50 examples satisfying y equal to 2, and out of them how many have x is less than 15? 45 have. So 45 by 50. Okay, this probability is 45 by 50 times what? Times probability y equal to 2. How many examples are there for which y equal to 2? Again, that you have already seen, 50. 50 out of what? 50 out of 200. Okay. So this gets cancelled out, 50 gets cancelled out, so you get 45 by 200, and similarly the other ones also. So basically, you are like all these quantities you are able to easily calculate just by looking at the data and just counting. You can estimate all these relative frequencies, and thus you get all these probability values, except for this proportionality constant k. That is, you know that probability of y equal to 1 given x is less than 15 is equal to some value times k. This probability is also some other value times k. The same with this one and this one. Okay. So the only thing that we do not know so far is k. Okay. Now, from what you can already see here, can you tell me how I can get k easily?
Sum equals to 1. The sum of the probabilities equals to 1.
Exactly. The sum of these, since this is a distribution over the label space, since this is a probability distribution, the sum of these probabilities must be equal to 1. So that means, like, I have like let this value be so what is this value? This is like 40 by 200, like means like 0.2, I guess. Yeah, so this is 0.2 plus k, sorry, 0.2k. This is like 45 by 200 times k. This is like 0.05k, and this is 0.04k or whatever, or sorry, whatever that is. And so basically I add them up and I get equal to 1, right? So like I can easily then solve for the value of k, right? So like k, so once I have solved the value of k, whatever that value of that constant is, I can just multiply, like replace the value of k here, and I will get all these probabilities exactly. Okay. So once I have got all the probability like all these probabilities, so basically I have got the posterior distribution of y which I wanted. And now what we may be interested in understanding is the relation between the prior and the posterior. So the, as I said earlier also, both the prior, this is the prior and this is the posterior. So both prior and posterior are distributions over the label space. So they, in a sense, they are comparable. So if you look at prior, the prior distribution, this is what it looks like. The prior probability that y equal to 1 is 0.4, and it is that y equal to 2 is 0.25, and so on and so forth. On the other hand, if you consider the posterior, taking into account that x is the feature is less than 15. Suppose after observing that the feature is less than 15, if you are considering the distribution on y, you may see that it has changed compared to the prior distribution. For in case of y equal to 1, the probability remains unchanged. Why is it the case? That's because for y equal to 1, that is x less than 15 and x greater than 15 are equally likely. Why so? Because of this. So the y equal to 1 examples are equally divided into x less than 15 or x greater than 15. So so if you, so whether x less than is less than 15 or x is greater than 15, that does not improve your knowledge, or that does not give you any new opinion about whether y should be like that is whether y is equal to 1. So y can be equal to that is the that is if y is equal to 1, both are equally likely. So like that is the probability of y remains unchanged in both cases. Now, but if but what about the probability of y equal to 2? That we find that if x is lesser than 15, then the probability of y equal to 2 increases significantly. From 0.25, it has gone up to 0.45. That means what? That means overall 2 was not a very frequent level. Only 25% of the examples had it. But if I know that x is less than 15, that is the attribute value is less than 15, then I think that okay, then why it is possible that y may be equal to 2. There is a greater chance that y is equal to 2. But on the other hand, if I know that x is greater than 15, then I am more certain that y cannot be 2. So the probability comes down like this. Okay. This is, and again, this is happening because that is a y equal that is among the y equal to 2 examples, most of them, in fact the vast majority of them, have x is less than 15, and only a tiny minority have x is greater than 15. So this imbalance is getting reflected in these two probability distributions. The similar claims can be made about y equal to 3 and y equal to 4. So like in if that is for y equal to 3, as you can see, its prior probability is 0.2. Now if I know that the attribute is less than 15, then the probability that y equal to 3 goes down even further. But if I know that x is greater than 15, then the probability increases a little bit. Same with y equal to 4. So so this way you are actually, like, depending on what your actual observation x is, that is what the feature vector x is, you can actually get a distribution on the feature space which may be significantly different, or maybe somewhat similar to your original prior distribution py, which was before taking any feature into account. So now, so this kind of, and now if you want to predict a single level, so now you have got a probability distribution over the feature space. So now if you want to predict one single level, obviously that like that is if you're like if the application is such that you need to predict one particular value only, then of course you will just choose the modal level whichever label has the highest probability, highest posterior probability, you will choose that label. So in this case, if your attribute value was say 12, then this is the posterior distribution you should consider, and in that case you would find y equal to 2 as the modal label because that has the highest probability. So in this case your prediction is going to be y equal to 2. But if x is like 23, and then this is what the case, this is the distribution you should be considering, and in this case you find that the modal label is 1. So you say that you can, in that case you will predict the label to be 1. Okay? But whatever you are predicting, you will have a confidence of making that prediction. So in this case the modal level is 2, but there is only 45% probability that y is indeed equal to 2. The other 55% probability is split among other possible values, but overall 45% may not be such a high probability. So here you have to specify that I think, you will say something like I think y may be equal to 2, but I am only 45% confident about this statement. Or if x is equal to say 29 or something like that, then you will say that I am confident, that is I think y is equal to 1, but I am only 40% confident about this matter. Okay? So whenever you are making, you are not only making a prediction, you are attaching a confidence score also along with your prediction. So the same thing you can do in case of logistic regression also, which we saw yesterday. Yesterday in logistic regression, we are seeing that the different classes have different probability values. So now, if I must predict one particular class, then of course I will choose the class with the highest probability, but I will also have to specify that probability as the confidence of my prediction. Otherwise, it will not, my prediction will be incomplete. Right? Because saying something with 80% confidence and saying something with 40% confidence are of course not the same thing. So you will have to specify that, okay, I think y is equal to 2 is the most likely class in this case, but there is a very significant chance that it may not, it may be something else also. So that you have to specify that, and if you specify that, and that may like help, like whenever you are making the prediction on behalf of some like important agency, giving this kind of confidence score is very important. So suppose I am going to, for example, suppose I am going to predict where a particular cyclone is going to make a landfall. Say suppose a cyclone is coming towards along the coast of Bay of Bengal, and and you have to predict on which state it will fall. Will it fall on Tamil Nadu or on Andhra or on Odisha or on West Bengal, or will it go away to Bangladesh? Right? So you have to make this prediction, but a lot depends on that prediction. If that is suppose you say that suppose you somehow predict that the cyclone is going to fall on Odisha, and then the Odisha government believes your prediction and takes a lot of precautionary measures. It evacuates a large number of people, etc., etc. But but the cyclone suddenly changes way and goes to West Bengal instead. Then it's like double trouble. Odisha government will think that all its effort was wasted. On the other hand, West Bengal government will be caught unaware, and there will be a lot of losses. So that is, but instead of predicting that it is going to Odisha, if you had predicted that you are 45% sure that it is going to Odisha, but there is also a 40% probability that it may go to West Bengal, then like both Odisha government and West Bengal government would have taken the measures appropriately. That is, neither would have been very certain. So that is, they would have been ready, but maybe the amount of investment they would have done to it on this matter may not have been so much. Right? So that is why giving a whenever you are making a prediction, especially if it is something critical, then it is important for you to specify the confidence as well. Okay? And this kind of prediction, probabilistic prediction is known as the Bayesian classifier. Now, what if we have multi-dimensional feature. So I was just telling you earlier with this very simple situation where there is only a single attribute value, and that also I binarize by choosing a particular threshold. That is, there is one attribute which may be taking values between 0 and 30, and I find that the median value is 15, so I use that median as a threshold. So effectively I have a binary feature. It's like, is it above 15 or below 15? But that's a very simple scenario. In general, you will have lots of features, and many of them in many of the cases you may like it binarizing it like this may not be easy. So what happens when you have multi-dimensional features like this? Okay, so let us take a simple example that x1 is there are two features or two attributes, x1 and x2. Okay, so now so when you observe any particular data point, you will observe both x1 and x2. You know what's the value of x1, you know what's the value of x2. So the question you will be asking now is somewhat like this: given that x1 is this thing and x2 is that thing, tell me what is the probability distribution over the labels. Okay, so this is what you need to calculate, right? Now if I go back to the board, so if I want to estimate it, so let us now look at the what our class conditional looks like. So clearly now the class condition, it's going to be somewhat like this, right? You now, that is probability y given x1 equal to let's say small x1, where small x1 is a particular value, and x2 is equal to small x2. So this I must write as somewhat like this: probability of x1 equal to small x1, x2 equal to small x2 given y times probability y. So this part remains unchanged. This is the prior. The problem arises with this part. So note that this is now it's a conditional joint distribution. Why conditional? Because like it is based on the condition that y is equal to something. That is, you are for a particular value of the class level y, you are trying to estimate the probability of this particular feature vector. Now why is it joint? Because now the feature vector actually comprises of multiple dimensions, each of which are to be considered as a separate random variable. So if it's a d-dimensional feature vector, like it's a joint distribution over d random variables. Okay. So then the question will arise: how do I estimate this kind of a joint distribution? Okay. So it turns out that you will have to estimate this again from the data. So let us say that this is what your data set looks like. So you will basically have to consider all the cases, that is, you'll have to count all the cases or frequency of all the cases. That is, in this case, for each of the cases, while, or I mean for each of the labels, y equal to 1, y equal to 2, y equal to 3, y equal to 4, you will have to, all the examples that are there, you will have to break them up into groups like this depending on their feature values, and then way only you will be able to estimate this joint distribution. Okay. So like how to do it? Of course, like again, that is again based on these relative frequencies. So estimating these, that is, once you have been able to write down this kind of a table, that is, from the data set, once you are able to construct a table like this, then estimating the probabilities is of course very easy. You just have to read off this table. So y equal to 3, you choose this column, then you choose that row which corresponds to these particular feature values. So in this case, it is this row which we must be looking at. So this 10 is 10 is the number out of what? 10 out of what? Or 10 by what? 10 by the number of examples for which y equal to 3, which is 10 plus 15 plus 15 is equal to 40. So this probability then turns out to be 10 by 40 times probability y equal to 3, which is of course 40 by 200. So Yes.
What is K in this equation?
So again, K is the proportionality constant. So like here also, just like it's like this posterior is proportional to the just a second. Yeah, so the posterior is proportional to the class conditional times the prior. So the posterior so since it's proportional to, then there must be a constant of proportionality. It does not matter what exactly that proportionality constant is, but but you will be able to estimate it easily by the same principle that you had used in the previous case. So for a particular value of the features, you will calculate the probability of y equal to 1, probability of y equal to 2, y equal to 3 and y equal to 4. In each case you will get k times something. So you will, and you know that since it's a probability distribution, they must add up to 1. So you will add them up, you will get an equation in k, you will solve for k and you will use that value here. Okay, this is straightforward. So this kind of classifier is known as the Bayesian classifier. So like as you can see, it has been it has been worked out for you also in this in these sheets. So I'm for the lack of time I'm not going into it, but the important feature to note here is that the feature like here, if there are d-dimensional features and each feature takes m values, right? So like in that case, what happens to the table size? So clearly this table, so in the previous case where there was one feature taking two value, we had two rows in the table. Now we have two features, each of them taking two values. So so how many rows we got? We got 2 into 2 equal to 4 rows. So similarly, as we have more and more features and those features keep taking more and more values, then our table size also blows up accordingly. So now you can easily work out that if there are a total d number of attributes like this, as we had been assuming earlier, and each of those attributes take m number of values, then of course the total number of rows of this table is going to be m to the power d. Okay? So clearly that's a very large number. As m increases and as d increases, that is as the even if m is equal to 2, suppose even if somehow you are able to binarize all the features, but as the number of features d increases, clearly it will become like 2 to the power 3, 2 to the power 4, 2 to the power 8, 2 to the power 10, 2 to the power 12. So you can understand how quickly the size of this table will blow up. And as the table blows up, the table size blows up, the more will be the number of probability values you will have to estimate. So so that will be a lot of work for you. So that's not computationally efficient. So what do? We make this assumption. What's the assumption? The assumption is that all the features are independent. That is, if there are d features, each of those features are taken as a random variables. Now I am claiming that all of them are independent of each other. That is, now if they are independent, that means what? That means they are, as we have already discussed earlier, if the features are like if they a and b are two random variables which are independent, then their joint distribution p of a comma b can be written as p of a times p of b. This is again basic probability. This is something we all know, right? If a and b are independent, this perpendicular which is sign which I have given in the context of probability, it denotes independence. Okay, so if a and b are independent, then their joint distribution can be written as the product of their marginal distributions. So similarly, in this case also I am doing the same thing. This is a joint distribution of two of two attributes. I can now write it as the product of the individual the probabilities of the individual attributes. Okay? So now you can see, so what did we gain by making this kind of an assumption? So clearly this may not be a great assumption to make, because the different attributes are often not actually independent of each other. So they are actually not independent of each other. So what did we gain this way? What we gained here is computationally, instead of having m power d rows in the table, the number the actual so now you can see that what you will basically have is that you will get d separate tables, one for each feature. Okay, and then each of those tables will have m rows. So the total number of rows you are getting this way is m times d. Instead of m power d, you are getting m into d rows. So correspondingly, so that's a large reduction, right? So instead of having something like 2 to the power 10, we are now having 2 into 10. That is, instead of 1024 rows, now only 20 rows will do. So that's a huge reduction of computation. So although if the assumption which you are making is probably very simplistic and probably not correct, but it helps you with a lot of computation. That is, a lot of computation is saved. So that is why this what we are discussing so far, that is called the Bayesian classifier. Now once we make this assumption, then what we get is a naive Bayes classifier. That's what this is known as. So now you can this calculation of this posterior distribution, you can calculate it in the following way, right? So this joint distribution, as you can see, you have broken it up into two separate distributions or two marginal distributions of the two features separately, two attributes separately. Each of them you can estimate from their respective tables, and then you can just calculate it. And so you will still be get a final posterior distribution on the class level. You will still have to make a that is whenever you are making a prediction, you will still have to specify a confidence, but a lot of computation will be saved for you. True, the results may be slightly bad, but experimentally on many data sets, it has been found that this naive Bayes classifier is actually giving results quite comparable to the original Bayesian classifier. That is, although we made that assumption that all the features are independent of each other, and that assumption may not be very accurate also, but still it turns out that as far as classification is concerned, on many real world data sets, it does not make much of a difference. The classification performance does not reduce. Instead, you gain a lot in terms of computation. So that's basically the second way of doing probabilistic classification after the logistic regression, which we discussed in the last class. Okay. So with that, we come to the end of the lecture on probabilistic classification. Now we will move over to the second part of today's discussion, which is going to be our discussion of the AI Shiksha platform, and after that we will discuss the assignments. So let me stop the recording now, and I will restart the recording for the next round. So